The Cobra maneuver, often called Pugachev's Cobra, is a high angle of attack maneuver in which a fighter briefly pitches up almost vertically, dramatically increasing its angle of attack, to decelerate and reposition relative to an adversary. Although originally popularized by the Soviet-designed Sukhoi fighters, various modern and even some older fighter jets have been engineered to perform such post-stall maneuvers. Below is a discussion of several fighters that have been associated with the ability to perform the Cobra maneuver and an explanation of the aerodynamic principles and control inputs that enable it. In the Cobra maneuver, the pilot suddenly commands the aircraft to pitch up sharply. This rapid pitch forces the aircraft's nose well above the horizon, sometimes near 90 degrees relative to the horizontal flight path. This throws the aircraft briefly into a post-stall regime. In this state, the aircraft spoils its traditional aerodynamic lift and forward momentum. The rapid deceleration, as aerodynamic drag rises dramatically, can confuse an opponent's missile seeker or allow the pilot to reverse roles in a dogfight. Advanced digital fly-by-wire systems, and in many modern designs, thrust vectoring, maintain control even when conventional aerodynamic stability is greatly reduced. How a fighter achieves it generally involves using full, abrupt stick inputs to pitch the nose upward. The Sukhoi Su-27 was designed for air superiority with high maneuverability. Its delta wing and tail design, combined with a high thrust-to-weight ratio, allow it to operate at high angles of attack. When executing the Cobra, the pilot commands a rapid pitch-up. Even though the airframe enters a post-stall regime, the carefully designed aerodynamics keep it controllable. An evolution of the Sukhoi Su-27, the Sukhoi Su-30, is a multi-role fighter that sports additional control surfaces and, in some variants, limited thrust vectoring. The Sukhoi Su-35 can execute the Cobra maneuver by rapidly pitching up, while thrust vectoring augments aerodynamic control in the near-stall condition. As a fifth-generation stealth fighter, the Sukhoi Su-57 features advanced aerodynamics, canard surfaces, and full thrust vectoring, making extreme post-stall maneuvers possible. The Mikoyan MiG-29 has a relaxed static stability design and fly-by-wire control systems, which help it perform demanding maneuvers. Being an older generation fighter, the MiG-21 was initially built for simplicity and agility. However, talented pilots have shown that a simplified version of the Cobra can be produced. The Draken, a Swedish fighter famous for its distinctive double delta wing, was designed for high speed and agility. Its aerodynamic layout provides a high angle of attack envelope, the Chengdu J-10B. This Chinese multi-role fighter uses a canard delta wing design, which enhances its agility and responsiveness at high angles of attack. The Dassault Rafale employs advanced flight control systems. Its canard delta configuration and fly-by-wire system allow it to operate safely at high angles of attack. The F-22 Raptor is renowned for its stealth, supercruise, and exceptional maneuverability. Its combination of thrust vectoring and advanced avionics allows rapid pitch transitions. Across these fighters, several common themes enable the execution of the Cobra maneuver. Many employ delta, canard delta, or other high-lift wing configurations. Modern fighters rely on digital flight control systems to manage inherent instability at high angles of attack, continuously adjusting control surfaces. Thrust vectoring allows engines to direct exhaust downward or to the side, providing extra pitch and yaw authority during the Cobra maneuver. Performing the Cobra requires precise pilot inputs. The maneuver involves trading airspeed for altitude and a high angle of attack. The pilot must carefully manage throttle, pitch, and control surface deflections to recover normal flight and maintain situational awareness. The Cobra maneuver is often the subject of intrigue because of its dramatic appearance, but its practical importance in actual air combat is rather nuanced. In demonstrations, the Cobra is spectacular, but in real-world combat, its value is more limited. It can force an overshoot or break away from engagement. One beneficial scenario is when a pilot needs to rapidly reduce speed to avoid an overshoot by an opponent's missile or to change engagement geometry. Today's air combat centers more on beyond visual range engagements, sensor integration, and network-centric warfare rather than dogfighting maneuvers. Modern air combat relies more heavily on energy management, advanced sensor integration, and missile combat rather than theatrical maneuvers alone. While the Cobra maneuver is a powerful tool in a fighter jet's repertoire, its practical application in combat is situational rather than fundamental. It is one of many high angle of attack tactics that can be employed under the right conditions. but it is not a game changer by itself. Moreover, modern warfare has advanced beyond dogfights. It is now based on stealthiness and ability to engage and take out your enemy without being seen. Thrust vectoring in aircraft refers to the ability of an aircraft's engine to direct the thrust in a direction that is not parallel to the aircraft's longitudinal axis. Essentially, it allows the engines to be used as a flight control surface, providing additional maneuverability, especially at high angles of attack or low speeds. How thrust vectoring works. Thrust vectoring involves directing the exhaust flow of the engine by using movable nozzles or other mechanisms. This redirection of thrust can be used to generate forces that control the aircraft's pitch, yaw, and roll. Benefits: enhanced maneuverability. Thrust vectoring allows aircraft to perform tight turns and other maneuvers that would be difficult or impossible with conventional control surfaces alone. Improved agility. It can increase an aircraft's agility, especially in close-range dogfights. Short takeoff and landing (ESTL) capability. Thrust vectoring can be used to create vertical or short takeoff and landing capabilities. Examples of fighter jets capable of performing thrust vectoring: the F-22 Raptor, F-35 Lightning II, and various Sukhoi fighters, Su-30, Su-35, etc., are examples of aircraft that utilize thrust vectoring. Comparison with conventional controls. While thrust vectoring enhances maneuverability, it's important to note that it's often used in conjunction with conventional control surfaces like ailerons, elevators, and rudders. Thrust vectoring can augment or replace the functions of these surfaces, especially in extreme flight conditions. To execute advanced maneuvers like the Cobra and those facilitated by thrust vectoring, fighter jets rely on sophisticated electronic systems. Here's a breakdown. 1. Flight Control Systems, FCS, and Fly-by-Wire, FBW. This system uses electronic signals instead of traditional mechanical linkages to connect pilot controls to the aircraft's control surfaces, for example, ailerons, elevators, rudder. In dynamically unstable aircraft, FBW is crucial for maintaining control and stability by allowing rapid and precise adjustments to control surfaces, even in situations where human input alone would be insufficient. Thrust Vector Control, TVC, also known as thrust vectoring. This system manipulates the direction of engine thrust to control the aircraft's attitude or angular velocity. It employs specialized nozzles or mechanisms that can deflect exhaust gases, providing control even at low speeds or high angles of attack where traditional aerodynamic control surfaces are less effective. Integration of FCS and TVC. The combination of FBW and TVC maximizes the aircraft's agility and safety. It enables pilots to execute precise maneuvers and offers enhanced capabilities in challenging flight conditions. 2. Digital Electronic Control Unit, DECU. Engine control. The DECU manages various engine functions, including fuel flow, airflow control, and the ignition system. Thrust vectoring control. The DECU directly controls the actuators responsible for deflecting the engine nozzles in thrust vectoring systems. Communication with other systems. It communicates with the aircraft's flight control system computer to ensure smooth and coordinated control. 3. Sensors. Flight data. A range of sensors, for example, airspeed, altitude, angle of attack, provide crucial data to the flight control system. Engine parameters. Sensors monitor engine performance and parameters, for example, thrust, nozzle position, to facilitate precise thrust vectoring control. 4. Actuators control surface movement. Actuators translate electronic signals from the FBW system into physical movement of the control surfaces, impacting the aircraft's pitch, roll, and yaw. Nozzle deflection. In TVC systems, actuators adjust the angle and position of the engine nozzles to redirect thrust. How these systems enable the Cobra maneuver pilot input. The pilot initiates the Cobra by disengaging the angle of attack limiter and pulling back hard on the control stick. FBW and TVC control. The FBW system interprets the pilot's input and, alongside the TVC system, commands the necessary control surface deflections and thrust vectoring adjustments to pitch the aircraft's nose upwards dramatically while maintaining a near constant altitude. The aircraft's aerodynamic design and the electronic controls ensure the aircraft maintains stability and control even in the high angle of attack, near stall condition of the maneuver. To exit the Cobra, the pilot adds power and pushes the stick forward, and the electronic systems facilitate the smooth recovery to level flight by adjusting control surfaces and thrust vectoring as needed. In essence, the Cobra maneuver and other super maneuverable capabilities in modern fighter jets are achieved through a seamless interplay between the pilot and advanced electronic systems like fly-by-wire and thrust vectoring. These systems translate pilot intent into precise actions, allowing the aircraft to push the boundaries of aerodynamic control and perform maneuvers that would be impossible with traditional systems.